In this video, we will talk about timers on the 8MEGA32. Firstly, we will talk about the concept of timers and then the sources of clocking, because we have two sources of clocking. We have external clocking and we have internal clocking. Then we will go through the timers registers in details, and finally we will took two examples of timers. So, what's a timer? Timer is it's like a counter, a counter that counts the rising or falling edges of a periodic signal. Uh, how this happened? If you see here this pulse, these pulses, each pulse of them have like a period. The time period begins from the beginning here of the rising age and ends on the beginning of the other of the pulse number two. Yani. So here, uh, this is the rising age because the signal or the value of the signal goes from 0 to 1, or the value of the clock yani itself, it goes from 0 to 1. So this is a rising age. And the falling age when the signal goes from 1 to 0. So when you make the timer, you make like a counter that counts the rising age or the falling age. Yeah, and you don't put pause on the equation. No, you put only one age, the rising age or the falling age. So if you want to calculate the number of counts, so you count, for example, here we have, this is the first rising age, second rising age, third and fourth. So you count the number of the rising ages. So, for example, here you have 4 counts. The time period is equal 1 over the frequency. So if you know the frequency of the system, so you will have the value of a one period time of the system. Here in 8MEGA32, we have the range from 1 megahertz to 16 megahertz. So we will use these values. So the time elapsed for the whole pulses, it will be n, which is the number of age counts. Whatever you decide to count the rising age or the falling age, time, the time period itself that you calculated from this equation to know the size of a one period. Okay. So this is the concept of having the timers. So if we want to make a timer that gives me a delay of, for example, 1 second, so we will determine the frequency of our system, and then we use this equation to know the time period, and then we'll see to calculate a 1 second using this time period, how many rising age or how many falling age that we will have, and then we will know the time elapsed for our delay. Okay. So, for example, if we having like a 1000 hertz, so the time period will be 1 millisecond. So if the counters have 10 millisecond, and this will be corresponding to 10 millisecond if the time period is only a 1 millisecond. So this this is the way that we operate the timers. So from the parameters, we should know now, we should know the frequency of our system, and we will get the time period from it. And we should know the time of counts that will represent the delay we want to make on our system, which is implemented by the timer. In the 8MEGA32, the default frequency, it's 1 megahertz. If we use the equation time period equal 1 over the frequency, we will see that the equivalent time period is like a 1 microsecond. So it's very small. Why it's very small? Because if we want to make a delay, for example, of the 10 milliseconds, so we will need in this situation, we will need like 10,000 counts. 10,000 counts, it will not fit on our 8-bit register. We know that the 8MEGA32 microcontroller is a 8-bit microcontroller. So every register on the memory, it's a 8-bit size. So now this value, which is the 10,000 counts, it will not fit on our 8 bits. So we will need a bigger counter. So from this point, the idea of the prescalings come up. And here there's an example that if we factor our frequency, what means factoring? Factoring means decreasing the frequency of the system. Yani, for example, here, if we have the frequency of 1 megahertz, and then we decreased the frequency by a factor of 64. So the frequency will be decreased to 15.625 kilohertz. And if we calculated the number of counts that will represent a 10 millisecond, it will be 157 counts. 157 counts, it can be represented by 8 bits, because the 8-bit is 2 to the power 8, which is 256. So from 0 to 255, it will this value, it will fit on our 8-bit register. So this is the reason that we use prescaling, to make the number of counts fit on our 8-bit registers. So now let's see how the prescaling happened. The prescaling, as I said before, that we decrease the frequency value. But take care that we will not decrease the whole system. We only decreasing or prescaling the frequency of the timer, not the whole system. The whole system is working with the 8MEGA32 frequency on the range from 1 megahertz to 16 megahertz. So this happened by using GK flip-flops. It's like 4 GK flip-flops. Each flip-flop, it make like dividing a factor of 2. We're dividing our frequency by a factor of 2. So here, if you see this signal on QA, if we introduced a clock pulses to the first GK flip-flop, so the value of our clock pulses will be decreased by a factor of 2. So as you see here, the time period increased and the frequency of the pulses decreased. And so on, if we pass by the signal to another GK, the time period increased more by a factor of 2, and the frequency decreased, and so on, till we come to the output of our prescaler, which is QD. As you see here, the time period increased by a factor of 16, and the frequency decreased so much. So here we rescaled or we decreased our frequency so we can achieve the frequency, achieve the number of counts that we need that will fit on our 8-bit register. Also, we have another source of clocking than the internal clocking. We can connect our 8MeGa32 to an external clock source, which is called external oscillator, external crystal oscillator. It's a component you put. This component will provide the 8MeGa32 with a clock with within the required frequency. If you want to operate the timer with a lower frequency. And this is the block diagram. We can also imagine more how this process happened. So here you have external bands on the 8MeGa32. This that we can connect our component to the 8MeGa32 band, and this multiplexer choose between the internal clock that is coming from inside the 8MeGa32, which has the range from 1 megahertz to 16 megahertz. This will be decided by the code, or it will choose the source coming from the external crystal oscillator that we connected from outside the 8MeGa32. So this multiplexer, by the help of the fuse low byte, will decide which source of clocking that it will be used, and then it goes to the prescaler register, and then to the clock system, to the timers. Now let's go to investigate the timers world. On the 8MeGa32, we have 3 timers. We have 2 timers, which is 8-bit size, and we have a 1 timer, which is 16-bit size. We have timer 0 here. This is 8-bit. And we have timer 2. And we have timer 1. So let's go to investigate the registers. We have here 5 registers that we will use for the timers. The first one is the timer counter register. This timer counter register is responsible for determining what's the value that the timer will begin with. So, for example, if you will begin with a 0, so you will write TCNT, and N here stands for the timer. So, as you see here in this register, if you use timer 0, so you will write TCNT 0. If you will use timer 2, you will TCN2, TCNT2, or 2CNT1 if you will use timer 1. So this will define the start of our timer. Then the timer begins to operate, and here it will decrease until it reached the value we want the timer will to end on. Here another register, which is the timer counter control register. This register has a set of functions. The first one that we choose whether we will use the internal clock source or the external clock source. Also, we determine the prescaler that we will use for the internal clock. And finally, we define the counting mode. We have two counting modes. We have maximum value and then reset, that the timer is counting from the beginning to until it reaches the maximum value of the 8-bit register, which is 255. And this is the first counting mode. And the second counting mode, we define a specific value for the timer when it reached the timer reset. So this is the two timer modes. And here let's see which will happen. Now, if you choose that you will use the internal clocking source, so here you will use three bits, the first three bits of the register, which is CS00, CS01, and CS02. So this is the table that define the values of the bits that corresponding to what we need. So, for example, if we want to prescale our internal clock to a factor of 64, so we have to put CS02, CS02 by a 0, and CS01 by a 1, and CS00 by a 1. So if we write the code, we will do that later. We should shift CS01 by a 1 and CS00 by a 1 to define the value. But here CS02, it's the value is a 0, so we will do nothing for it. Then here we will use the two bits, which is the WGM00 and WGM01. These two bits, we define the counting mode of the timer. If it will be a count till maximum, then reset, or it will count till a certain value that we defined, then it will reset. The second one, it's called clear timer on compare match. And it have a common abbreviation, which is CTC mode. So if we will choose the default mode, so the WGM00 and WGM01, it will be 00. But if we choose the mode of the CTC, which is clear timer on compare match, so we have to put WGM01 by a 1, and we can use the masking technique that we learned before, or the shifting to put this bit by a 1. Also, there is two bits that we will need if we choose the clear timer on compare match mode, which is the CTC. This output signals, we will use it. There is a signal called OC, output counter. This signal, it's used only on the mode of the CTC. This is the values if we want the this is OC signal. We will use it later also on the PWM and the servo motor labs. So we can control by these bits the values that goes to the OC pin. It's like an output pin on the 8MeGA32. So with these bits, we control the value that goes to the OC. So here, if we working on the normal port operation, so the output compare bit will be disconnected. But if we working on the CTC mode, so this bit can be toggled 0, 1, 0, 1, 0, 1. If we put these two bits, the COM01 and COM00 by COM01 by a 0 and COM00 by a 1. But if we want to clear the OC0 OC0, because we for example, if we use timer 0, so it's called OC0. We put the COM01 by a 1 and COM00 by a 0. But if we want to put it by a 1, so we will put 1 and 1 on the COM01 and COM00 bits. And here is the bins of the OC. So here, this is bit OC0, which related to timer 0. And here is OC2, which is related to timer 2. And for timer 1, timer 1, we said before that it's a 16-bit timer. So it's like taking a two registers. So it has two OCs. We have OC1A and OC1B. Because we have an output bit for each byte, which is the 8-bit register. This register is called output compare register. This register is special if we are working on the mode of CTC or clear timer on compare match mode. Here we said that in this mode we specify a specific value that we want our timer to reach. Okay, so if we want our timer to reach to make a delay of 1 millisecond, so we have to calculate what's the number of counts that equivalent to this 1 millisecond that we have said on the beginning of the timers, that we have to determine 3 parameters. We have to determine our frequency of the system. We have to determine the time period from the equation, time period equal 1 over the frequency. And also we have to determine the number of counts that equivalent to the time that we want based on the time of a one time period. So here in this register, we put the number of counts equivalent to the time that we needed for our delay. But we have a limitation that this number shouldn't be more than 255, which is the maximum value of the 8-bit register. Okay. So also to use this, we have to choose on the register of the control register, which is that we have explained it before here. We have to choose that that our counting mode will be CTC before we can use this register. This register is the timer interrupt flag register. It's responsible for indicating that the counting is still proceeding, or that the counting or the timer has ended counting and it will reset. So let's see it. Here, this is the register. We have for the timers, each timer have a flag. It's called timer overflow flag. So here, if you see this, this is TOV0, which is timer overflow flag for timer 0. If the value of this bit is 0, that means that the timer not reached its maximum value. But this is for using the normal mode, not the CTC mode. And so if this bit is 0, so the counter not reached its maximum value. But if it goes a 1, so this flag will indicate that the timer reached its maximum value and it resets. So this is for using timer 0 on the normal mode, and this bit for timer 1, and this bit for timer 2. But on the other side, if we used the mode of the CTC, so here we will use these bits, the OC bits, output compare flag bits, this bit for timer 0. So if timer 0 not reached the specific value that we put, which will be represented by the counts that we'll put it on the output compare register. So this value will be a 0. This flag will be a 0. But if we reach the specific value of the counts that we put it on the register compare match, so it means that the timer has reached the specific value and it reset. This is also for timer 2, the same function. But as you see here, that timer 1 has 2 bits, OC1A and OC1B, because we have a flag representing each bits. And also I want to say this note that each one represent this is represent the lower bits, and this is represent the upper bits. The last register on the timers is the timer interrupt mask register, and from its name, it's not used on the normal operation of the timer or the making a delay, a certain delay, but it's used only if we used the interrupts. So we enable the interrupt bits also for this with this register, and it also has 2 modes. We can use the interrupts on the normal mode, and we can use the interrupts on the CTC mode or the clear timer on compare match mode. If we are using the normal mode, so here we have 3 bits that we can enable it to make the interrupt works with the timer. For timer 0, we use this bit, TOIE0. This is for timer 0, so if this bit is a 0, so 0, so that means that the interrupt mode is not enabled. But if we put it a 1, that means that we enabling the interrupt. This interrupt happened when the timer reaches its maximum. So For example, if you want to make a delay, and when the delay ends, a certain LED turned on. So to make this by using the normal mode, which is that the register reaches the maximum value of the counts, which is 255. So you will put this bit by a 1, so the interrupt is enabled, and then you can insert the interrupt function, and based on that, when the timer reaches its maximum value, the interrupt it will goes to the interrupt function, and the interrupt function will turn on the LED. Also, here we have a bit for timer 1 if we want to enable interrupts with timer 1 on the normal mode, and this is for timer 2. For using the other mode, which is the CTC, or the output compare match, this bit's called output compare interrupt enable. The output compare interrupt enable bits, as you will see here, we have this one, output compare interrupt enable for timer 0. So if we put here a 1, so we enabled the interrupts with the timer for timer 0, and OCIE2, this is for timer 2. But for timer 1, we know that it's 16-bit, and it has places for 2 registers, lower 8 bits and upper 8 bits. So here we have 2 bits to enable the interrupts for them. If you want to enable the interrupt for the lower bits, so or the you will use the OCIE 1A or OCE 1B. So this is a part, this 2 bits also represent the 16-bit timer on our 8MeGA32 timer 1. Okay, let's go to lab tasks examples. Now we will implement the delay function that we created by a line on the previous labs with the timers. So if we use like a delay of 1 millisecond, so we will see how to use it on simple blinking LED code. We made it on previous labs. So step 1, we want to initialize our registers. The first register is the time counter control register. This register, as we said before, that it has many functions. The first function that we use it to determine two things related by the clock. We determine which source of clock that we will use, internal or external, and if we use internal clocking, so what is the prescale factor that we will use. So if we choose to use the internal clock and a prescale of 64, so and our timer frequency, we know that the minimum frequency of the 8MeGA32 is a 1 megahertz. So if we calculate the time period, it will be 15.625 kilohertz. And if we want to make a delay of 1 millisecond for our blinking code, it will be represented by only 16 counts. So this is the number of counts that we will write on our output compare register. So to choose the internal clock and the prescale, we have to initialize these two bits of the timer counter control register by these values. So as you see here, CS02 equals 0 and CS01 and CS00 equal 1, 1. So we have to write a code for this sake. We will use timer 0, so the timer register, which is the timer counter control register, it will be TCCR0, 0, which is stands for timer 0. And then we will use the masking technique because we want to affect only these bits on the register, and we will use the shifting to put bit CS01 by a 1 and bit CS00 by a 1. Then we want to choose which counting mode that we will use. We will use the normal mode, or we will use the clear timer on compare match or CTC mode. So if we put the values WGM00, it will be a 0, so we will not overwrite it. But the WGM01 equal 1, so we will set the value of it by a 1 by writing TCCR 0, 0, timer 0, ordered with a 1 shift WG01. Then the register, which is output compare register, because we choose that we will use the CTC mode, and this is logic because we want the timer to reach a specific value. We don't want the timer to reach the maximum value of the register. We want a specific value, which is the 1 millisecond, that is equivalent to the 16 counts. So for this sake, we put the value for the register output compare register, the OCR. Also we use timer 1, so it will be 16 counts. So we will write OCR 0 equal 16 counts, which is equivalent to the 1 millisecond that we calculated from a while. Then step 2, we want to see our outputs. We'll make a blinking code. So for blinking, we have to first we have to define the direction of our ports. We will use port A. So for using port A, we have to make the direction of port A output by writing on the register of the direction, which is DDR. DDR stands for data direction register A, because it's related to port A, equal 0xFF. 0x hexa means hexa, FF, which is 8 ones. And we will initialize the port A by a 0, 0. For this code, we don't have any inputs. It's only a blinking mode, and also in this code we will not use interrupts, so we don't need it. Let's write the code. First, we will write the headers that we will use it. So for using the I/O ports of the 8mega32, we have to include the header file #include avr /io.h if we will use the interrupts, but here we will not use interrupts. We can use this header, and the delay functions. Also in this code, we will not use the delay functions. We will make our delay, and there are some functions for checking the bits. We can use it to check the values of the bits of the ports. So we will include this header file, which is hash include avr slash sfr underscore defs. Then here we want to write the delay function. Our delay function, it's a normal function. We will put it outside our main function and then call it on the main function code. So it's like a for loop. This for loop limit is the number of milliseconds, which is the value of the time that we want to reach. And here is a loop until bit is clear, which is a function defined on the sfr underscore defs header. This function makes sure that while the OCF0, which is a bit on the timer on the timer flag registers is a 0, so this means that the timer not reach it to the specific value that we write it on the OCR register. So it will loop here on this for loop, and when the timer reached the specific value, this OC will be a 1, and we will go out the delay function, and so on. If it's called, it will work again, and so on. This is the initializing of the timer registers. We have explained this before for the TCCR0. This is the prescale, how we prescale the frequency to 64, and this is how we choose the counting mode, which is CTC, and this is the OCR0 value, which is 16 counts, equivalent to a 1 millisecond delay. Here is the main function, and this is the while one loop that we write all port A by a 1, so it will turn on, and then we toggle it by using the XOR masking. So it will goes from 0 1 0 1 0 1 0 1, and here we used the delay function that we implemented on the previous slide. This is the whole code. Don't forget to define the system frequency here, and this is the delay function that I explained before, and here's the code. Let's go for another example which we use the interrupts. So here we will use two timers. We will use timer 0 and timer 2. Timer 0 will be used as it is in the previous example for the delay function itself, but timer 2 we will use it for the interrupt. The interrupt service routine should turn on a LED for 5 seconds. So if we call the delay function, so the delay function will make the counting, the delay of the 1 millisecond, and then when it goes to the interrupt routine, a LED will be turned on for 5 seconds, and then it will return back to the main function and continue the code. So here we will make the same steps that we made on the other example, but also we will use the same steps for timer 2. So we here also we used the same prescaling of 64. For 16, for timer 0, we use 16 counts, but that represents a 1 millisecond. But here, for the interrupts, it should be on for a 10 millisecond. So the number of counts here will be 160 counts, not 16 counts. So the OCR 0, it will be having a 16 count, but the OCR 2, it will have a 160 counts. And both we will enable the CTC mode for them because we want to reach a specific value. And here the OCRs, we used OCR 16 because here this is the number of counts that represent a 1 millisecond, and for OCR 0 and for OCR 2 we used 160 because this is the number of counts that represent 10 millisecond. We also have the same values for the function because we still have the same code for blinking. Here we are using interrupts. These interrupts are coming from timer 2. When timer 2 reaches at 10 milliseconds, so it will go out of the interrupt function. So here we have to use the last register that we explained before, which is the TIMSK. TIMSK, if we recall it, the timer interrupt mask register, if it works on the output compare interrupt, the output compare interrupt enable bits, it will be our interest. And to enable timer 2, so we have to use this bit OCIE2. OCIE2 have to be written by a 1, so we can enable the interrupt for timer 2. So if we go back to the code, here we choose the CTC mode for this timer, and at the same time we enabled the bit which is the OCIE2, which I showed you on the register from a bit, and we put a value of a 1 in this register, and also we enabled the global interrupts on our. This is all the header files that we need. I explained it. And here is the interrupt function. We used the timer 2 com vector. So we will use the timer 2 on a CTC mode. And here we used port B for connecting the LED of the that we will turn it on for a 5 seconds. And here we use the delay function and put 5,000. This is the code. It's the same of example 1, but we added up the same specs for timer 2, for choosing the prescaler, for choosing the clocking source, and also here we choose the CTC mode, and we added up the number of counts for timer 2, the OCR2, it will be 160, and here is the interrupt mask. We enabled the interrupt for timer 2, and this is the global interrupts function. So this is the whole code. This is the header files, and this is the delay function that we use it for the timer 0, and this is the interrupt function. We use it for timer 2, and this is the rest of the code. Any question? You can send me an email, and thank you.